In the last video, we talked about how to integrate the following function. So we had integral of z times dz, and that was our integral. And then we were on the following path. So the curve was 1 plus I to 3 plus 3i. It was a straight line segment, and we found that the value of this integral directed along that curve was equal to 8i. So that was the result we obtained from the last video by doing the parametrization of on that straight line segment. So now in this video, what I'm going to do is I'm going to show you how to apply the independence of path to find line integrals. So we're going to get started with the following example. So we're going to have a straight line segment once again, but this time this line segment is actually going to run from 1 to 3, and it's going to be constant along the y direction, so it's going to be horizontal. Let's call this curve C1 so that we differentiate it from this one. And now we have the points 1 plus I and 3 plus I. So those are the 2 points that we're integrating with respect to. So we're going to apply the same procedure. We have the variable z equals x plus iy, and we want to represent x and y in terms of a parameter t. So in this case, what we can do is let's make x once again our independent variable. So let's have x equals to t, because remember, x is actually changing. We have a different value of x between these 2 points. So x is going to be our independent variable. And now let's have y is going to be equal to, once again, the straight line equation, which is mx plus b. But in this case, we notice something very peculiar. The gradient of this line is just 0. And then what would be the y-intercept? Well, the value of y is just constant at 1, so that means this is just going to be 1. And that implies that y itself is going to be equal to 1. It is going to be a constant horizontal line. So now that we have those 2 definitions, we need to determine the limits of integration. Well, we already said that the limits of integration for a line integral are going to be equal to the limits of integration of the independent variable. In this case, it is x again, so t is going to be bounded by 1 and 3, just in the same way as here. So you can consider that if we were integrating with respect to a real function, and we were finding the area underneath that curve, this would be the limits of integration of that. Alright, so now that we have defined that, we can finally write our expression for z, which is going to be z is equal to t plus I, because y is just 1, and then this z is going to be the derivative of this with respect to t, which is 1, and this is just 0, so this is just going to be 1 times dt. So that's very straightforward. And now we're going to plug that back into the integral. So we're going to evaluate the same integral now, but with respect to the curve 1, which is this one. So we can have z dz, and this is going to be equal to the following. So limits of integration. Now the function, the complex variable z in terms of t is t plus I. And then we're going to have this z is just dt. So this is very straightforward. We can integrate directly. And now we're going to have t squared over 2 plus it. And then this is going to give us the following. 9 on 2 plus 3i minus 1 on 2 plus I. So what are we going to get from this? Well, we should get, if we combine the real and imaginary parts, we should get 4 plus 2i. So this is the answer to this problem. That's the line integral of the complex function z of this z along that curve. Okay, so we have this result. Now let's have the following example. So I'm gonna delete this. Let's get rid of this. And let's consider another example that is going to involve parametrization of a curve. So let's have the following. Let's have xy. Now I'm going to have a vertical line segment. So it's going to go to the point 3 plus 3i. This is going to be 3 plus I. So it's directed along that. Let's call it C2. So this is 1, this is 3, and this is just constant here. Alright, so what can we do here? Well, this is the same as flipping this over and calling x a function of y, because remember, x is just going to be constant here, so x is just equal to 3. And then what is y? Well, y is changing, so we can call y the independent variable. And it is going to be equal to what? It is going to be, well, let's define this instead. Let's call y equal some independent variable t. And let's have x equal to my plus b. So we're going to apply the same thing that we used before. So if we flip this on its side, if we have x here and y here, then hopefully you can see that this is 3 and then this is 1, 3. Right? So this is the same as flipping it. So in terms of that, the gradient is 0. And x is just constant at 3. So that means that x equals to 3. And now we have t is going to go from 1 to 3 once again, because the bounds of integration are now defined by y. And then what we can do with this is we can define the integral. Well, before we do that, let's have z equals to x plus iy. And in this case, we just apply this. So it's going to be 3 plus ti. That means that dz is going to be equal to I times dt. So now we're going to evaluate the integral along C2 of the function z. And this is going to be 1 to 3 of 3 plus ti times I dt. So we can expand this out, we can multiply that I by these two terms, and then we're going to get the following. We're going to get 3i minus t dt. And this is going to be equal to, so 3it minus t squared over 2 from 1 to 3. And then if we plug these values in, we're going to get 9i minus 9 on 2 minus 3i minus 1 on 2. And hopefully you can see that this will turn out to be minus 4 plus 6i. So this is the result for this particular curve. Now, why did I go through this whole process? Well, let's have a look at this. So the curves I chose in these two examples are very peculiar because they actually relate to the first example we solved in the last video. So we started off with this curve, which we called C, which went from the point 1 plus I to the point 3 plus 3i. And in the last two examples, we actually defined two curves. The first one was horizontal. We called it C1, and then this one C2, which went to the point 3 plus I. So we defined this one as that, and then this one as that. So the independence of path theorem from line integrals tells us that the integral from this curve should be equal to the sum of the integral along this plus this one. And is that true? Well, let's see if this is true. Z dz equals to C1 Z dz plus integral C2 Z dz. Let's see if that is actually true. We found for this integral in the last video that this was equal to 8i. And then we just found that for this one we had what? We had 4 plus 2i. And then for this one we had what? We had minus 4 plus 6i. So obviously this and that are going to cancel out, and in the end we're going to end up with 8i equals to 8i. So immediately you can see that yes, independence of path is actually satisfied in this case, and in fact it is satisfied for any curves that you choose. We could have easily chosen something a little bit more extravagant. So instead of a two straight lines going like that, we could have chosen something like a parabola or a smooth curve like that, and we should have gotten the same answer. So that's the beauty of this property of line integrals, and you can see that we can extend it to integrating functions of a complex variable. And in the next video we're going to continue with more examples of parametrizations and evaluating contour integrals.